Happy New Year, all of you. And today we are going to see a very exciting result on irrationality and physics. So let's see how physics speaks and comments on the behavior of irrationality of real numbers. So let's take a very fundamental situation. Let's say we have a circular table with center O, and we start at a position A. Let's imagine we have a small ball of mass m which starts at a point A and is thrown in the direction as shown in the diagram. The motion is frictionless, and once you start, it will continuously, indefinitely go on the circular table, because once it hits the edge of table, it will reflect. Next reflection might be somewhere else, and we have a second reflection, third reflection, fourth reflection, fifth, sixth, seventh, eighth, 9, 10, and so on and so forth. So it will fill the entire table with this. Since the motion is frictionless, and in the first case we are going to assume the collision to be perfectly elastic, it means there is no dissipation of energy. So the kinetic energy throughout the motion is going to be constant, so you will not see velocity decreasing, and hence the motion will continue forever. So kind of immortality in the motion of the particle. The question starts like this. Let's say the first row is such that the angle that this chord make with the center is alpha. So we have to see the dependence of the trajectory of the ball on alpha. Okay, so how the trajectory is going to be based on the initial condition of the angle alpha. This is a mixed problem. Both of you can think from mathematics point of view as well as physics point of view. The basic physics is quite a general science here, which I've already discussed, like we are assuming motion to be frictionless and collision to be perfectly elastic. So let's take a very simplest situation to analyze this before we go further. What will happen if you take a ball and try to project directly to the center? So as we can clearly see, it will hit the table at a point B. At that point, according to law of reflection, so let's say if you have a surface and a ball is thrown in this direction, at the point of contact we have normal over here. So according to law of reflection, angle of incidence and angle of reflection will be equal, provided the surface and the ball is having perfectly elastic collision and no dissipation of energy, obviously. So since we know for a circle the normal will always pass through the center of the circle, hence the angle of incidence in this case is 0. Hence the ball will continue to move along the diameter forever. So after B, the ball will come to the next point A. Again after A, it will go back to B, from B back to A, and so forth. So it's kind of periodic motion which is going to happen. Let's analyze when we throw it at another angle of, let's say, 120 degree, before we go further with a generalized idea of an angle alpha. So if I throw a ball in such a fashion from the point A such that this angle is 120 degree. So clearly from the diagram, since these two radius are equal, this angle to be 30 and 30 degree each. Since the collision is elastic, so the ball at the point B will reflect back with the same angle, 30 degree. This is the case because we have perfectly elastic collision, hence angle of incidence and reflection is going to be same. I'll come on the coefficient of restitution as well, which tells the angle of approach and angle of descent separation is going to be same. So after 30 degree inside, still at that point you can see it's making 120 degree because of resistless property. So next collision, again it will go to 30 degree. And now since this is 30, So if I, this angle must be 30, and clearly we can see we have A, B and C, we have equilateral triangle over here. So after collision from point C, the ball must hit the point A. It means if I start with the angle at the center with 120 degree, we'll have exactly 3 collision before it come back to its original point A, and the ball will continue to move on a triangle. So on and so forth. We can do it for even 60 degree angle or 40 degree angle, 15 degree angle, and so on and so forth. So let's generalize this configuration for a general angle theta at the center. So we got a ball at point A thrown at point B, so that the angle that this motion AB, the first collision is making, let's say that is alpha. Let's call this angle as phi and phi. So after first collision, because of elastic collision, it will deviate with the same angle called phi, because OB behaves like a normal. And you have a tangent which is tangential to the circle at a point B. So this phi angles is going to be same. Again, we'll have next collision. Here you have phi, and so on and so forth. Thus, the angular position of the successive point of impact, as you can see, A, B, B, C, and C and something, is all subtending a same angle alpha at the center. Okay, so now we can basically distinguish between two types of trajectory. So there will be two cases. If this alpha around the center sum up to be exactly equals to pi, right? So let's say we have p times of alpha for some integer p, alpha plus alpha plus alpha p times, if it's totally becomes an integral multiple of 2 pi. So let's say that is q times of 2 pi. If that happens, can you think what will be the situation of this trajectory? So for the sake of simplicity, you can see if alpha were 120 degree, so we have 120 degree into 3, that is exactly 2 pi, which is 360 degree. So if this angle, some integer multiple of this angle is exactly 2 pi, or maybe 4 pi, or 6 pi or 8 pi, the significance of 2 pi is you started the collision, the ball was thrown from point A and is coming back to point A in one cycle. If it's 2 pi by 3, which is 120 degree, into p equals some multiple of 2 pi, then it means p represents number of collision, right? Because in 3 collision it makes a 2 pi angle, in 6 collision it will make 4 pi, in 9 collision it will make 6 pi, and so on and so forth. So q times 2 pi, this denotes the total amount of angle which you are making at the center. So for q to be integer and p to be integer, the practical significance of p is number of collision. So p denotes number of collision, because in every collision we'll have an alpha angle at the center. So in p collision, the angle which is made at the center is p alpha. If that becomes integral multiple of 2 pi, the ball will be back to the point A, right? Because exactly that alpha and alpha angle at the center will be made, so the trajectory of the ball will be such that it's coming back to point A, right? So you can clearly see like it's going to be a parallelogram if for number of collision is 4. If number of collision is 3, we have an equilateral triangle. If number of collision is, let's say 5, we'll get some pentagon, which will be in regular pentagon, regular hexagon, and so on and so forth. So the condition at p alpha equals 2 pi q, that gives the necessary and sufficient condition for a ball to come back to its identity, to its original point. And now you can clearly see what it means is if alpha is 2 pi q by p, or 2 pi by alpha is p by q. By definition, p and q is integers. Here I have chosen to be positive integers, because maybe there is no meaning, physical meaning associated to number of collision which is less than 0. So if this is a rational number, the rationality means that the ball is coming back to the point from which it is thrown. What if this becomes irrational number? So let's say if you have number of collision is p and alpha, and now that's not equal to 2 pi q. So let's say if the initial angle is pi by root 2. If alpha value is pi by root 2, so the number of collisions that will have is 2 pi by root 2, which is going to be 2 root 2. Right, so the significance of this result will be when 2 pi by alpha is not equal to p by q. It means the ball will not come back to its original configuration as shown in the original figure number 1, original diagram. So the significance of irrationality is like the motion continues forever in a different track, and you never get to know the exact footprint of the ball where it's going. So the predictable motion is kind of unpredictable in the sense like the trajectory is not a closed path of finite length, right? So the takeaway is when the ball has returned to A, the trajectory is a closed part of finite length and the motion is periodic. But if alpha is equals to times some irrational number, the angle of rotation of the point impact with the wall is not 2 pi times the integral multiple. Hence the ball will never return to the starting point and the trajectory is going to be open and non-periodic. So this irrationality signifies open trajectory and non-periodic motion. The rationality here signifies closed trajectory and periodic motion. Now I'll take a while. Let's say if you have a number, let's see how this event is associated with the rationality of a number. If you have got a number 1 by 2, so we know this number is 0.5. So number has already died here. So rational numbers are those numbers which has terminated, which ends. Or we can have another variety of rational number where 1 by 3 is 0.3333. So you can see like this is periodic kind of motion. So the 3 is repeating in a length of 1, which is exactly the diameter case of the situations. Like just with one side, the things are repeating in the rationalization case. So it corresponds to, you can simulate this as if it corresponds to this kind of sequence. Okay, we can have rational number even 0.12, 12, 12, 12, 12, and so on and so forth. So it represents the still periodicity of this number 1, 2. And the loop is closed. Loop is closed in the sense like you already know exactly what track it will be having. What about irrationality of a number? If we consider root 2, it's going to be 1.414 something. So now there is no periodicity in this number. There is no pattern in this number. So the path is not flowing a periodic motion. There is no periodicity here. Moreover, it is a non-ending path. Non-ending in the sense even every time the ball moves, where 2 pi q is not a multiple of p alpha. I mean 2 pi by alpha is not an rational number. So in that case, the path will be really irrational. So we'll have irrationality in the movement. In the sense it's non-terminating and non-repeating. The path is not repeating, and moreover obviously it's non-terminating. It's never dying. Even in irrational number, that will be the significance of the ideas. So what we have concluded is for the rational number, either the path will die, so energy will be fully absorbed, or it will show a definite pattern. So it's repeating but reoccurring. For irrational number, you can see every time the ball moves, it will move on a completely new path. So there is no fixed pattern of the path that we can predict in terms of this simple experiment. and moreover is still immortal, so the motion continues forever. So this was one of the interesting example which shows you how fundamentally we can conceive the ideas of irrationality and rationality with a basic physics example. Now let's move to a case where we incorporate let's come to the case where we sacrifice the perfect elastic collision case. So now let's come to the case where we sacrifice the perfect elastic collision case, and let's bring some energy absorption on the surface as well. So let's repeat the same example with a more general approach. So now we have a smooth billiard ball is projected from point A. So still we have a ball projected from point A on the edge of a circular table in a direction making an angle phi with the radius. So after first projection kilo, let's call this angle is phi. The coefficient of restitution is E. So now what does it mean to have? So E is coefficient of restitution. Coefficient of restitution basically signifies the absorbing factor. So when the ball and the surface is not perfectly elastic, so some part of the kinetic energy will be absorbed by the surface because of surface deformities. This is how basically we model it. So to account for the absorbing energy on the surface, we define something called coefficient of restitution, and it's quite commonsensical. How will you define it? So now in this case, since if a ball is thrown like this, some part of this will be busy in like breaking this a small elevated surface. So ball is not expected to go exactly perfectly in a symmetrical direction, so maybe it will be deviated from the law of reflection now. So in this case, if angle of incidence is I, we don't expect angle of refraction to be R, rather angle of refraction will be different from angle of incidence. So in the language of physics, they define coefficient of restitution as the velocity of approach and velocity of separation, that ratio. So how much the ball is being resisted by the surface is fundamentally the idea behind the coefficients. So let's do it from a mathematical perspective more. So after ball collides at point A, it will go to some point, let's say C, and now again it will keep on continuing. So let's take one case when the ball makes Q impacts with the wall before returning to A. Suppose after Q reflection from the ball returns to A. So let's take a very small case of Q equal to 1 first. So for Q equal to 1 and E is the coefficient of restitution, what will be the value of phi? So it's quite clear. For Q equals 1 means if number of collision is 1, there is just one impact before the ball comes back to A. So in that case, the ball must be projected along the direction of the center, right? So if I project the ball A passing through, after reflection it will come back to A and this will continue forever. So for Q equals 1, the value of phi is going to be 0. Next condition is what if Q equals 2. So if we have 2 reflection and ball comes back to its original position, under that condition what will be the value of angle phi? Basically we know like this angle phi will be related with the coefficient of restitution, right, and the number of reflection of course. So let's analyze the case when we have the value of Q as 2, which means we have 2 reflections before it comes back to its original place. So let's project the ball with some velocity B. We have center O, and now we know if we'll connect this, these two angles will be equal because of being isosceles. So let's say these angles are phi. Now after reflection it will not no more be equal to phi, so let's call this angle is some phi 1, and clearly the velocity will change. So let's call the velocity is v1. Velocity has changed because the collision is not elastic and some part of the kinetic energy is lost in deforming the surface, or so called in changing the potential energy in the form of elastic energy of the surface. So after B1, the ball moves back, and according to the situation, we want to find a condition where after two collisions, this is first collision at B, second collision at C, ball has to go to point A. So this angle is going to be still phi 1. So this angle is going to be still phi 1. Again, let's say it comes with the velocity of B2 with an angle of phi 2 over here. In the previous situation, all these phi 1 and phi 2 were equal, but now there will be difference on this angle because there is difference in energy because of energy absorption. So if it has to go to the path back to A, so in this case we can clearly see how phi 1 and phi will be related. So we can do basic geometry. This angle is going to be pi minus 2 phi, this is pi minus 2 phi 1, and this is pi minus 2 phi 2, because sum of angles of triangle is 180 degrees. So if we'll add all of them, we have 3 pi. So if we'll add all of them, we'll have 3 pi minus 2 phi plus phi 1 plus phi 2 is going to be 2 pi, corresponding to this case of equals 2, which gives you 2 times of phi plus phi 1 plus phi 2 equals pi. Now for the impact at B, if we'll use the conservation principle or conservation of momentum, if I use for an impact at B. So at this point, we have a tangent and we have got a normal which is passing through point O. So what is the angle of the conservation of momentum? Since there is no net force in this direction, along the tangential direction, the net force sigma net is 0. So we can apply the conservation of momentum along the tangential direction. Along the vertical direction, like along normal, we have clearly normal force. Okay, so because of this normal force, the change in momentum along that direction has occurred. Since mass of the particle is same, so the velocity has suffered a change, and hence the angle of incident and reflection action. So that's the basic physics. If we'll see the Newton's law, and basic momentum will be conserved, so mass times velocity along this direction. So if this angle is phi, we know this angle is going to be pi by 2 minus phi, right? Again, the angle of reflection, this one is pi by 2 minus phi 1 from the geometry of circle, because on a circle a tangent will make 90 degree with the radius vector. Since the ball was moving in this direction, so if we'll decompose the ball direction, we'll have one vector over here, other is there. So vector along normal direction will be v cos pi by 2 minus theta. Since mass of particle is m, so initial momentum along tangential direction is mb cos pi by 2 minus phi. And the final momentum that we are getting along this direction is, now the ball is going away from the surface B, so it's taking away some part of momentum along the tangential direction, which is mb1 cos projection of b1 along this tangent is pi by 2 minus phi 1. So that gives mb1 cos pi by 2 minus phi 1. Mass gets cancelled and we have a nice equation, cos 90 minus di sine theta. So v sine phi is b1 sine phi 1. Now it totally makes sense, because you think of the elastic situation when velocity is equal, where energy is conserved and phi 1 is same. Now in this case, can you comment on which angle will be more? So clearly the velocity will decrease because of the energy loss. So v1 is less than b. So if b1 is less than b, we have sine phi by sine phi 1 equals b1 by b, and this quantity is less than 1. So sine phi is less than sine phi 1. And here in the diagram, these angles are acute. So if we concentrate on 0 to, let's say, 90 degree case, so as sine increases, the angle increases. So since sine phi 1 is more, so phi 1 is greater angle than phi. So it's quite interesting, like the ball will not only deviate, but also it will deviate with the higher angle of reflection. So if you have got a circle, the ball incident angle, let's say if it is 30 degree, the angle of reflection will be maybe 40 degree. So it's going to deviate further. It has happened because of the absorption, so the normal reaction is not able to push the ball exactly more in the direction of normal. Okay, so the normal direction force is basically in our laser, which makes it more biased towards the tangential direction. Because the natural tendency of the ball, if surface were not there, would have been to go in this direction. Okay, so it will travel straight. So now more and more inelastic collision will be there. More it will try to shift to this direction. It will try to go towards its original configuration. Right? If it is perfectly elastic, it will try to go exactly at the 30 degree. Okay, so this is equation number 1, which practically and physically means something to us. So now we are convinced that a relation between velocity and angle is v sine phi equals v1 sine phi. Now we have another relation which can be done usually in the experiments with guided information, which is coefficient of restitution. So what is coefficient of restitution? It's the ratio between, I have told, velocity of separation and velocity of approach. And that equation is different from this equation in the sense like E is a measure of the energy loss factor kind of. So what is E here? So velocity of approach, as you can easily see, it is this velocity, which is fundamentally v sine phi, and the velocity of separation is v sine phi 1. So here if you are going to write the equation, E is going to be velocity of separation, which is v1 Okay, so now we have another parameter which fundamentally tells like how much energy is observed. And you can clearly see, since we have already found equations in the tangential direction, so we need to take care of another physical principle along the normal direction to the circle. So we want along this direction some equations should be written. And it is along normal direction which suffers the change in the the velocity or kinetic energy of the particle. So by what factor the kinetic energy has reduced, that depends on the irregularity of the surface and surface interaction of ball and the surface. And that is captured very nicely with the coefficient of restitution. So what is coefficient of restitution? It's a ratio of velocity of separation by velocity of approach. The surface, if we draw the surface, this was the velocity v1, v with an angle phi, and it came out with the velocity v1 with an angle phi 1. Now clearly we can see the velocity of approach in the first case is v cos phi, and the velocity at which ball has emerged from the surface, so that component is v1 cos phi 1. Now v cos phi and v1 cos phi 1, that must be different because the velocity has suffers the change because of energy dissipation. Hence the ratio v1 cos phi 1 by v cos phi, this captures the feeling of the reduction in speed or reduction in energy. And this is defined to be. So now we have got two equations. Equation number 1 is v sine phi equals v1 sine phi 1, and equation number 2 v1 cos phi 1 equals ev cos phi. So if we divide this equation, we got tan phi 1 equals 1 by e tan phi. So we know now exact relation between the given the value of e, which comes from experiment, we know the ratio of these angles, right? Similarly, we can do the same activities at an impact point C. So this we have done the activities at point B. We can repeat the same fundamental physics for point C, and now you can replace these parameter just with different phi. So at point C, if you'll see the collision, we'll have 10 phi 2 equals 10 phi 1 by E, and that will give you 10 phi by E square. We have one more relation between the angles. So phi 1 plus phi 2 equals pi by 2 minus phi, and that gives tan of phi 1 plus phi 2 is cot phi, which amounts to 1 by 10 phi. So clubbing all these informations, we are not just doing mathematics, we are trying to make sense of what does it mean to solve physics problem. So 10 phi 1, 10 phi 2 is going to give you 1 by 10 phi. And now very happily we can substitute the value of 10 phi 1, 10 phi 2 here, and that will give E 1 by E 10 phi. 10 phi 2 is 1 by E square 10 phi. And we have 1 minus 10 phi 1 and 10 phi 2. So that's 10 square phi by E cube. 1 by into 1 by square. And this is going to be 1 by 10 phi. And now from here we can, so this is a relation between coefficient of restitution and what should be the initial angle phi for which exactly 3 collision will be made for E equals E. Now does this equation make sense? So take away 1. Take away 1 is very clear. For a particular value of E, if you solve this equation, we are tempted to get a value of phi, right? So we'll get value of angle, which will give you the answer. Now some of you might tell like there are infinitely many angle. In fact, the infinitely many solution corresponds to just the difference of all those solutions of phi, which is a multiple of pi, right? Because if phi is a solution of this equation, 10 pi plus phi will also be the solution of the equation. So 10 to pi plus phi will also be the solution to that equation. That simply simplifies that you are still on the same locus, right? So given value of P, we can easily check, we can easily find the value of 10 phi. Now we also know like if E equals 1, the collision will be perfectly elastic. So in that case, you can solve for the equation for T equals 1, and we have 10 to 10 phi by 1 minus 10 square phi is 1 by 10 phi, which gives 2 10 square phi equals 1 minus 10 square phi, implies 3 10 square phi equals 1. So 10 phi equals plus minus 1 by root 3. Usually we don't take negative angle because it shows that it's an opposite clockwise sense. So if I take positive, even negative angle implies the same physical situation. So phi is going to be 30 degree, which is pi by 6, and that exactly matches with our initial discussion of the physics, because if phi is 30, we have 30 30 120. So for elastic collision in 120 degree case, as we have seen above, the particle will come back to its original position. So the takeaway was very clear. From here we can clearly see how the angle is suffering the change, unlike elastic collision. So here phi 2 is going to be take away 2 is more than phi 1, and that's more than phi. Unlike the previous case where all these three angles were equal. So I hope you must have enjoyed this. You can repeat the same thing for 3 collisions, where in that case you are going to get you can repeat the same thing for 3 collision. In that case you are going to get some quadrilateral which will come into picture. Okay, so again you can do the same rituals of taking phi 1, phi 2 and phi 3 and establish the same relations over here. So I hope you enjoyed this lecture. Until that time, bye bye.